Morning, everyone. How are you? Do you have any questions about syllables or something that we talked previous time about? So hopefully today's lecture will be much more boring than the previous one. The screens will show whatever they need to show, and the computers will work and record whatever they need to record. So today's lecture is practically background on something that you definitely should know. It's basic arithmetic and algebra, and some trigonometry, some complex numbers, basic things from typically you probably learn that in science school somewhere, maybe the courses of the university. But we will take some additional angle to graduate angle to it. So we will look at all these things from a little bit higher abstract perspective and not just computational playing with numbers, kind of thing which you typically do in other courses where you just get some formulas, you put some numbers into the formulas and you get some answers. So you have much more beyond that, just putting numbers into the formulas. Okay, so we will talk about what algebra is really for algebraists, people who do algebra and not just solve questions in schools. Okay, we will talk about numbers in a different way. And I don't know if we'll get to theory of sets, but we will talk about nomenclature from theory of sets. We will not get into all the deep theories. We will not get into proofs or anything like that. And theory of sets is practically basic language of math that you will see in most of the articles. All of the scientific articles are using that notation from theory of sets, so you need to know all the symbols and other things that you will just meet and you need to know what they mean. Okay? So arithmetic is something which is related to calculations of different numbers. You adding numbers, subtracting numbers, dividing numbers. So all the operations with numbers is arithmetic. And you have natural operations like adding, subtracting, and so on. So algebra is very different in the sense that this huge jump up mentally. And it took a lot of time to get from arithmetic to algebra. And again, I know that in school you learn algebra still as continuation of arithmetic just with variables. Think about it like letters A, B, C as numbers, and then you add them, subtract them, do all kind of things with them. Right? So it's still like you learn it still as advanced arithmetic in a sense. But algebra in reality is something else. It's completely different mental state, and it took like thousands of years to get there for people to understand what is the meaning of algebraic operations, because the effort which they put was huge, and this is how they shifted the focus from numbers to operations. They started to think what kind of manipulation you can do on numbers and what kind of results you can get from it regardless of what numbers you use. This is the overall like abstract idea of algebra, where you can talk not about properties of numbers, but properties of operations. So we will talk only about few of this type of properties, just to show you as example like what I mean by that, because it's still like waving my hands too abstract. It's not very specific what I'm saying right now, but you just need to know that this is huge jump from just manipulating numbers to manipulating operators. And this will be very important to get into that mode of thinking when we get to linear algebra, because we will not think about matrices as just a bunch of numbers. We will think about that as some operator operates on some data, and it transforms the data somehow, produces some manipulation, and we will learn the properties of these manipulations. Not like how you compute matrices. This is not linear algebra, of course, okay? In linear algebra, you learn like techniques, how you manipulate numbers. Here we will learn what is the meaning of these operations. Just much more important for applications where we need just to understand what kind of manipulation we need to do. And then you will fit the right manipulation to the numbers, okay? So let's start talking about a particular property which is called closeness of operation. So closed operation means that no matter what numbers from particular subset you choose, you manipulate them with that particular operator, which could be just plus sign, addition operator, okay? And you always get result in the same subset. So for example, you're taking a subset of all positive integer numbers. Okay, 1, 2, 3, 4, 5, all the natural numbers. They are called natural numbers, counting numbers. If you add two counting numbers, regardless of what these numbers are, you always get counting numbers. Like if you add two integers, you always get integer. Right? It doesn't matter what integer you choose. So this is algebra. So this is, I don't care what numbers you choose. I'm talking about property of addition. An addition is closed operation on a subset of numbers, which is integers. Right? So for positive integers, it's always true. For subtraction, this is not closed operation in positive integers. Right? Because, like, yes, 5 minus 2 will be still integer and positive. But 5 minus 8 will not be in that subset of positive integers anymore. So subtraction is not closed. And this is how people started to expand systems of numbers for other types of numbers, because they couldn't find like closeness of particular operations, like subtraction. So they started to invent negative numbers, which initially made no sense to humans at all. And this was true, like negative numbers first appeared probably before Christ era, type of more than 2,000 years ago. But in Europe, it was not accepted until like 1700s, something like that. And people thought that this is completely wrong. So these negative numbers that we now use and used to use, okay, we got used to them. And now we do not think about them as something impossible. But even famous mathematicians of their time, and if you heard about Descartes, he is a very famous mathematician, and he invented a system of rectangular coordinates, analytical geometry, one of the fathers of calculus, and you have all kinds of things on his name as well. And probably if you learn outside of the United States, you name the rectangular coordinates Cartesian coordinates. It's from his Latin name. This is the Renatus Cartesius. This is an Latinization of his French name. Okay, so this Cartesian coordinates, rectangular coordinates. So he invented all of that. And as you understand, in Cartesian coordinates, obviously you have negative numbers, positive numbers, even in 2 dimensions. Right? It's a rectangular system of coordinates. But the thing is that he said, these numbers do not exist. They cannot exist. This is nonsense. Not right. We cannot use them. But at that time, it was completely fine to say, like, no negative numbers. You'll have only positive numbers, no negative numbers. Same thing with Pascal. No, Pascal, he is known for also a million different things, also a theory of probability, binomial coefficients, triangle of Pascal. You have, obviously, if you run physics, you have also units of pressure on his name, pascals. You measure pressure in pascals. Okay, so he's pretty famous, and he's famous philosopher, objective geometry, invented that thing, conic sections, they invented that thing. He has a lot of things on his name, okay, theorems. So he said that this is nonsense. You cannot use negative numbers. Nonsensical stuff. But now we understand and we got used to it. We use always negative numbers. And if you're taking all of the integers, this operation, like 2 minus 4, or between any other integers, will be closed in the set of integers. Not positive integers, but all integers. So now we expanded the set of numbers that we can work with, right? And now this operation became closed operation. So this is how typically mathematicians expand systems of numbers. They just look for problems that they cannot solve otherwise, okay, like subtracting any numbers, any integers. Then they say, like, well, let's try to invent something new which would make that operation closed. And this is algebraic type of thinking. And in linear algebra, you have same type of thinking always, where you want to expand it to the maximum possible level to describe maximum possibilities for everything we want to describe. Okay, this is how we think about them. So it's, in a sense, jump in a mental level of how you think about things. It's important to get into that mode. All right, so in arithmetic, all of the addition operations are closed within all natural numbers, 1, 2, 3, 4, 5, and so on. Subtraction is always closed operation within integers, which are positive and negative and zero numbers, okay, not whole numbers. And then multiplication is repeated addition. And this came from needs to work on areas. When you need to measure area, you multiply one side by another, you get total area of the kind of rectangle, okay? And this operation is always also possible within integers. Doesn't matter what integer you multiply by another integer, you still get integer. But it doesn't work for division, which is also kind of natural operation, inverse operation from multiplication. Sometimes you can divide two integers and to get integer, and sometimes you can't. So you need something which is practically fractions or rational numbers. It's one number, one integer divided by another integer, which is not integer. So it's fraction. So this is how you expand the field. Now, to make that possible, to make division always possible, you need to expand it also to all the fractions which are rational numbers. All right, except division by zero, which is prohibited. But not just prohibited. There is meaning to the prohibiting things in math in general. Why you cannot divide by zero? Why do you think you can't divide by zero?
Result will be infinity.
Yeah, we define that in calculus as infinity. It's kind of approaching infinity in a sense. But in arithmetic, you just can't do that, okay? Your calculator will show error. So why is that?
And multiply anything by zero to get the original.
Right, so the idea is that math should be not self-contradictory. That's an additional like abstract idea. What contradictory means, it should follow logic. So if you define division as opposite operation from multiplication, which is like if A multiplied by B equals C, then C divided by B equals A. And this definition of what division is, okay? So you define it by multiplication. So if you divide by zero, practically that would mean that A times zero equals something which is not zero. But this is contradiction, because you know it is zero, it has to be. Because anything multiplied by zero is zero. So you get contradiction here, so you cannot define what happens when you divide by zero. It could be any number, practically, all right? So it's like prohibited, you do not do that. But other than that, in the subset excluding division by zero, this operation is closed in a sense, okay? Now we have additional needs, like how people expanded, and I'm going through historical perspective on that just to understand how people stepped from one idea to another idea to the next idea, and why they even decided to do something to expand systems of numbers to something more sophisticated and deep, and something that we use today, and we, again, got used to it. We do not think about that anymore. We just use it as is, but there are like thousands of years of history here, how they got to all of them. So they needed to measure Earth, okay, for agricultural needs. Fields, to measure size of the fields, diagonals of the fields, other things of that kind. And this is where geometry is coming from, because geometry is geometry, like two roots, which mean Earth, measure. Okay, measuring Earth is geometry. So the question became like, is it enough to have only rational numbers to measure anything you want to measure? Especially as they started to work with a lot of triangles, other things like that. So what we know from that is diagonal of triangle with sides 1 and 1 will be square root of 2. Again, now we use square root of 2 as you do not think about like what actually it means with square root of 2. Is it rational number? Could you write that as fraction of some integer divided by some other integer? So you can't. And you can prove it in relatively simple proof. I will show it in a second. But the idea is that rational numbers are not enough to describe everything you want to describe in geometry. Because diagonal of that simple triangle
will not be rational. You will not find any fractions. You can approximate. You can find close enough fraction which is close enough, as close as you want practically to that number, but it will never be the square root of 2, because you cannot write square root of 2 as any fraction. So fractions are known to have two properties. One property, they are finite, so they have finite number of digits in decimal representation, or they have infinite period, which means you have some set of numbers which is repeating itself multiple times, like 5.223, 223, 223, 223, and so on, like period of 3, which is repeating forever. So this could be also rational function, rational fraction. Or you can have some sort of infinite period, like 9999999 forever, but it's never, it should repeat after a while, okay? So it could be like very long period, but it still needs to repeat somehow. Irrational numbers are different. They never repeat the same pattern inside themselves. They do not have like 5.732 and then some period. No, they always change, okay, forever. And different patterns all the time. Some of the patterns might repeat themselves within the kind of infinite sequence of digits, okay? But then you will get some other numbers, okay? So it's not random, obviously, but it looks like random, okay? All of these digits, infinite number of digits that you have. So this is irrational numbers. And why they are irrational, why you cannot write it. This proof was known probably for 2000 years, maybe even more. So here is that simple proof. Let's assume that it is true that this number is rational number, which means you can write that as m divided by n, and m and n both integers. Let's assume also that both of them are positive, so we're talking about positive root, okay? And that this fraction is reduced already. So you don't have like 2 divided by 4, you have like 1/2 instead. So you reduce, you always can do that. But you always can reduce it completely, so it's not, you don't have any multiplier in both of them, the common divisor, right? So it's reduced fraction. So these two numbers you cannot divide and simplify the fraction anymore, okay? So you take in that thing, I will show, you see my cursor? Yes, okay. So you write that square root of 2, and you prove that by contradiction. So we want to get to a particular thing which is not true from that assumption, right? So if you will assume something, and then you will show that it's impossible, then this assumption cannot be true, right? So we assume that m divided by n is rational fraction, and the square root of 2 could be written that way. So let's multiply both sides by n. So n will cancel here, and it will be n times square root of 2 equals to m, right? Now, so you are saying that n times square root of 2 equals to m, so you can do square on both sides. You'll get 2n squared equals m squared. Okay, so far, basic algebra, right? But now, what does it mean? It means that m squared is even number, because you're multiplying that number by 2. If you multiply any integer by 2, you have to get even number. So m squared is even number. But what does it mean that m squared is even number? What numbers squared are even? So let's start with 1 squared, not even. 2 squared, even. 3 squared, 9, not even. 4 squared, even, and so on. So every second number is practically even. So only even numbers squared are even. Odd numbers squared are not even, ever, okay? Which means that m itself is even, right? But if m itself is even, you can write that as 2k, so 2 times some other integer, okay? So it will be 2k squared here, so it's like 4k squared. So 4 and 2 cancel out. So you get n squared equals to 2m squared, which says exactly the same thing about n as we did it for m. So n should be even then, okay, as well, not only m. But we assumed that it's reduced fraction. Both cannot be even, because if both are even, you can divide by 2, each one of them, but you can't, right?
You see the logic here?
So
If n is even and m is even, you have canceling fraction. You can divide by 2. And m to simplify the fraction.
but our assumption was that this is reduced fraction. So it cannot be. So you have contradiction here, which means that no fraction whatsoever, no n or m, can give you square root of 2. And you can do same things, square root of 3 or some other numbers. Now, this is the idea of proof for rationality and irrationality of particular numbers, where you know that you need to expand that set sum. The square root of 2 is irrational number. And from the name itself, you can already hear that people dislike that kind of expansions of numbers. So you had negative numbers, right? Like negative. Or you have numbers which are irrational, like not making any sense. Or numbers which are imaginary numbers.
In complex numbers. So people even gave it like
Pretty bad names to show their bad relations with these numbers. But again, now we just got used to them. We still call them the same names, but we do not give them the same perspective because we use them every day and it's fine. Yes.
So reduced fraction will always have an odd numerator. Reduced fraction.
Two numbers, no, not necessarily. Like one of them needs to be odd, one even, or
Okay.
two odds, but they do not have common numbers that you can divide by. Like it could be 3 divided by 7, or it could be, let's say, both of them cannot be even, okay? Because if they are both even, then you can divide both of them by 2. Okay? It could be like 4 divided by 5. They don't have both to be odd. Okay, any other questions? And then after a few centuries, people came out with new types of numbers which are still irrational, but they cannot be even roots of any algebraic equation with rational coefficients of any kind. Numbers like pi, numbers like e. So you know many of these numbers, but you have like infinite number of these transcendental numbers, which could not be even written as roots of anything. Cubic roots, square roots, any kind of roots. Any algebraic equations, okay? They cannot be solution of any algebraic equation. So you have actually infinitely many that type of transcendental numbers which you cannot write as roots. And pi is very famous, and e is very famous out of these numbers. And this was proven only in 19th century, first time, end of the 19th century actually. First time there was proof of transcendentality of the pi number, which was big deal and very difficult proof. So mathematically, it's very complicated, so I'm not showing that. Von Lindemann was the first one to prove that. Okay. So here is a summary of all of the numbers that we talked about so far, and we will move to complex numbers. And complex numbers will be the most related to linear algebra because they are kind of subset of matrices in a sense, and you can maybe surprisingly use matrices to define complex numbers, 2 by 2 matrices, define complex numbers, specific matrices, particular matrices. And people typically do not learn it, not in linear algebra and not in complex numbers, but this is just interesting field. So we talked about natural numbers, which is 1, 2, 3, 4, 5, and so on. Sometimes you call these numbers with 0, you call them also whole numbers. But for all practical applications, I would call n including 0, and many textbooks actually include 0 in the natural numbers. They do not use it actually like n0 or n whole numbers. So sometimes you see natural numbers defined with 0 and sometimes without 0. Depends on the definition. From my perspective, like you can include 0 in n, okay, in natural numbers. Then you have integers, which are all of the positive and negative numbers, but whole numbers. And then you have rational numbers, which all of the previous numbers, it includes all of the integers and fractions. And then you have set of real numbers, which include rational and irrational numbers, which is like all of the possible numbers in real domain before you get to complex domain. But there was a problem of solving some of the equations, some quadratic equations, some cubic equations. People couldn't solve, for example, x squared equals -1, and they wanted to. But this was not the problem, because at that time they said like, well, no solution, not big deal, right? Not every algebraic equation should have solution.
In a sense, right? You don't have to define solution for something which is not existent.
Why would you even think about solving equation like x squared equals to minus 1? It's not defined, right? No solution. That's fine. People lived with that thousands of years, with many more thousands of years after that. But here was a problem. In probably like 16th century, people started to solve cubic equations. And then cubic equation, and this was like Tartaglia, Cardano, other European mathematicians who started to think about like how to solve cubic equations. Why they started to solve cubic equations? Because at that time they could get a lot of money for it. They practically mathematicians got their salary, if you wish, by participating in all kinds of competitions. Who can solve problems that nobody else can? Type of competitions. So they had all of these big European competitions given by kings of Europe of that time, and like this was like fame type of thing for them as well, if they can solve something that nobody else can. And cubic equations became at that time, for quadratic equations, they had formula, how to solve it, so it's not interesting, anyone would do that. But for cubic equations, they didn't have any formula that would give them roots of cubic equation. So each one of them contested others with providing them some cubic equation and saying like, if you solve that within like months, and you figure out roots of that thing, then you win. And you have that type of competitions between mathematicians. So what happened is that this guy Tartaglia, he invented formula for solving cubic equations when the solution exists in real numbers. So he has that formula, which was huge secret, and he tried to hide it. And then Cardano convinced him to reveal the formula to him that he will never say anyone ever. Super secret formula. All right. And then this guy published it. All right. So this is how we know the cubic formula. So he lied. All right. But this is a different story. The thing is that in that formula, you have roots of negative numbers. Okay. And the solution might be completely real. Like the answer, like roots of the cubic equation would be real roots. But to get through that formula, you need to compute roots of negative numbers which cancel out somehow. To have one root of negative 5 minus same root of negative 5, so they cancel out and you get some real answer. But the formula itself includes this roots of negative numbers. Okay, you cannot avoid it, you cannot get rid of that kind of thing. And then they just for convenience started to call it like letter I, square root of minus 1, just for convenience to use in that formula. It's like something which is imaginary, and they called it imaginary, okay, not real, imaginary. And then it cancels out, so we don't care what that imaginary thing is, just for convenience sake, okay? So, for example, and we will solve that example later, you want to solve difference equation. And we solve different equations with multiple different methods. We do all kinds of manipulations on that. And as you can see, all the coefficients are integer coefficients. So it's everything is real, no complex numbers anywhere. And this equation is like present state, x, present number equals twice the previous number minus twice previous number. All right, this is recursive type of definition. This is difference equation. You want formula for x of n, which is explicit formula for x of n. So I'm giving you the solution, which is xn, which is practically also real numbers. So cosine function is real function. All of the n's are integers. Square root is irrational, but still kind of real number. And power of square roots also real numbers. No complex numbers whatsoever anywhere. The problem is that you cannot compute that formula without having complex numbers. This is a problem, okay? Because the solution is coming from complex numbers, not from any kind of other real computation that you could do. You cannot find that formula without having complex numbers. And you have like million of other problems where you just cannot have any solution without having complex numbers. Because there is no technique in real numbers that you can apply that would solve that kind of problem. Okay, so you have many problems which are connected to imaginary numbers, and now all of the electricity we learned is all the imaginary numbers, and now we understand better even what it means. Okay, so practically we will see that multiplication by I means just turning the vector by 90 degrees. This, you had geometry behind it, okay? And this geometry was invented by Gauss much later, all right? Gauss lived probably like 200 years later. All right, so a few definitions on complex numbers. Any questions so far? We are doing kind of historical excursion into how numbers develop. So definition of, and we use J and I, just because we are electrical engineers. Electrical engineers using J instead of I, mathematicians using I for definition of imaginary number. So to solve that equation, we say this is that kind of square root of -1. This is our solution to that, which we still don't know what that means. So we also define complex number, which is a blend of real number and complex component of that real number. So it will be A plus BJ. Okay, so this will be complex imaginary component, and this will be real component. You add them together, and you need to know definitions of real, which is RE, and imaginary, which is IM symbols, okay? That's how you write real and imaginary. So pay attention that B is the imaginary part and not BJ. You do not include J in imaginary part. So both function real and function imaginary are real numbers. Do not include J. Okay, so this part is BJ, but only the B is imaginary part. All right. So you have also powers of J here to remind you. Hopefully you've seen that before, but maybe don't remember. So just to brush up your information about complex numbers. So J to the power of 0 as any other number would be 1. J to the power of 1 is J itself. J squared by definition is -1 because this is how you solve it. Like J squared is -1. J cubed is -1 times J. So it's minus J, right? To the fourth power, it's minus J times J, which would be minus J squared. So it's -1, so it's 1, all right? J fifths will be again J, and so on, and it repeats itself forever with all the other powers. So it has that cycle of going from 1, J minus 1, minus J, and then again 1, J, minus 1, minus J, and so on with higher and higher powers of J. Any questions on that? You can compute powers of J. We'll use it. Now you have also rectangular coordinates definition for complex numbers. So you can think about A and B as coordinate point in rectangular coordinate system, okay? And then you can think about that as a vector A plus BJ. So this is alternative Gaussian definition of vector and point in space. So this is our complex number. It will have also radius, which is size of that vector, and it will have angle from the real axis, angle of complex number. And this will be polar representation of complex numbers. So you have rectangular representation, which is like A plus BJ, and you have polar representation, which is radius and angle. And sometimes you also using like radius times exponent of J angle, which is, we will see why. Okay, this alternative, same thing. Any questions? All right. So let's do some trigonometry first, just to see, again, to brush up a few things, a few definitions, sine, and all of the other things, and conversion from degrees to radian. So to convert from radian to degrees, you're just dividing by 180 multiplying by pi, because pi angle corresponds to 180 degrees. Okay, so that's just proportion. And the other way around, you're just dividing 180 by pi multiplying by theta in degrees, you get theta in radian. Since we will be using both, so you need to kind of remember how you convert one into another. And this is the same thing that you are doing in code. If you want to convert angles from radian to degrees and back and forth. All right. So if you're thinking about right triangle, like that, with radius r, This will be A, this will be B side in the triangle. Cosine is defined as A, which is closest side of the triangle, by the hypotenuse. How do you pronounce it? Hypotenuse? Okay. So A divided by R will be cosine. B divided by R, which is the opposite side by hypotenuse, will be the sine, and tangent is B divided by A, and you can show that very simply that sine divided by cosine equals tangent. Why? Because this is B divided by R divided by A divided by R and R cancels, you get B divided by A, which is the definition of that function. Additional formula that we'll be using is sum of cosine square and sine square, which is always 1 regardless the angle. And the reason is very simple, it's just Pythagoras theorem practically. You can compute it from here. So you get A squared plus B squared divided by R squared, but R squared is A squared plus B squared from Pythagoras theorem, right? So you have that cancellation, and you get 1. All right, we will need Z because we will use exponent, which will have that kind of same description. So just remember that sum of squared cosines and sines is 1. Any questions? Okay, to add complex numbers is very simple. You just add them component by component. So you have C1 plus C2, which are 2 complex numbers built from A1 plus B1J and so on. You just add A components and then you add B components and you get something like that algebraically. Same thing will be with vectors in linear algebra. You just adding them component by component, right? And then geometrically, it will look like parallelogram rule, where you add in 2 vectors. So one vector will have coordinates C1, another vector will have coordinates C2, okay? In rectangular system of coordinates, the sum will be that parallelogram vector, which is yellow-brown type of addition of 2 vectors, as you do that in physics or some other areas. You add 2 vectors, you get the parallelogram rule, and this is where the coordinates will just add. Same thing. It's just geometric intuition behind it, like how you geometrically add vectors. And in algebra, it will be the same thing. You'll have 2 vectors, you will add them, you will get that kind of thing. Any questions on that? Now, subtraction is practically addition of negative vectors. So you can invert the direction of the vector, and to add that vector, so geometrically, it will be adding negative vector, if you want geometry of subtraction. So this will be, for example, C1 minus C2, that red vector. Because if you add in C2 plus that red vector, you will have C1. Okay, this is like going that way and then that way, you get that vector. It should be here. But algebraically, it's actually much simpler than geometrically in that sense, because they just cancel out. All right, multiplication is a little bit more complicated, and division even more complicated in rectangular coordinates. But it all follows simple arithmetical rules of multiplying different things, and the rules that J squared is -1. That's it. This is all you need to know about it. So you have A1 plus B1J times A2 plus B2J. So you multiply A1 by A2, A1 by B2J plus B1J by A2, like all of the combinations, right? You're opening the parentheses practically. So you get all of that, and here you get J squared. So you just replace it with -1, so it will be minus B1, B2. So it will be A1, A2 from here, minus B1, B2 from there, plus that thing multiplied by J. Okay, so this will be real part, imaginary part, multiplied by J. So this is how you multiply things. Now for division, you need some sort of trick. You need to multiply numerator and denominator by conjugate. And conjugate is A minus BJ instead of plus, okay? So when you multiply that kind of thing by conjugate of itself, you get actually a real number. Because when you multiply conjugate by the number, you get real number. And this will be the number because these 2 things are canceling. You get A squared and B minus B squared. And J squared, so it's like minus minus. It will get you A2 squared plus B2 squared. And then that thing on the top. Okay, this is how you divide in rectangular coordinates. Typically, we will not do that because too much work and too much to remember, I guess. So what we want is polar representation for multiplications and divisions. Typically, it's much easier, much simpler, and this is how it goes. So we replace A and B coordinates by radius and theta. We will define theta as arctangent of B divided by A, because tangents of theta is B divided by A, so you can compute it that way. And radius will be, again, Pythagoras theorem is like A squared plus B squared equals R squared. So you can compute R like that from Pythagoras theorem. So that's how you convert. Now to convert back, you just invert those relations and you get A equals R times cosine theta and B equals R sine theta. This is how you compute back to rectangular coordinates from this simple relations that we've seen just a second ago, okay? There are a few theorems by Euler, also very famous Swiss /
Russian mathematician.
he lived most of his life in Russia. So he invented that very famous theorem. It's almost like a definition for complex numbers in polar representation. So exponent in the power of j theta equals cosine theta plus j sine theta. Okay, this is how it works. This is the theorem. So if you want conjugate of that thing, you do just minus theta here and minus theta there. So sine of minus theta is minus sine of theta, and cosine of minus theta is just cosine of theta, because it's even function and odd functions, right? Cosine is even function, sine is odd function. So like in even functions, negative part is mirror reflection of positive part, and in odd functions, it's like anti-reflection, okay? Upside down reflection. So this is how you know that you just need to subtract here instead of addition, or to have minus here to get conjugate. Also, using solution of that system of equations that you have here, you can define cosine and sine using exponents, complex exponents. So cosine will be sum of complex exponents with positive and negative j theta divided by 2. And sine will be subtraction of positive and negative divided by 2j. It will have that additional complex component to define sine. We will be using these formulas in a little bit. And this is why I'm showing them. This course will not use too much of that kind of stuff. It's just to have smooth transition to remind you a few theorems, okay? So here's how you multiply in complex domain. Let's say you have those two complex numbers. This is your first complex number with radius and theta. Second complex number, you multiply in the radiuses and you add in the angles. Okay, this is how you multiply. Division is as simple as that. You just divide in the radiuses and subtract in the angles. Okay, sounds simple, much simpler than all these formulas with rectangular coordinates, okay, for multiplication. You can also do powers, also very simple. You just multiply that power by that power, and radius also in that power. There's r to the n, and exponent of nj theta. That's it. This is how you make powers. Roots, same thing, because root is kind of power of 1 divided by n, in a sense, right? So it's just multiplying by 1 divided by n, so it will be that kind of thing. So geometric interpretation of that exponent of j theta. Practically, the value is kind of moving with theta on unit circle. So it's complex number, e to the j theta, where we take angle theta, the radius will be exactly 1, so it will be unit circle, right? And this angle will be just moving on that unit circle. So when theta is going up, this thing is moving against counterclockwise direction on that unit circle. This is what e to the j theta is. It's just number, somewhere complex number on unit circle. This is what it is. And we will show that in the next slide, but what happens is that when you multiply, for example, numbers, you get much longer vector and angles are added together when you multiply them geometrically. This is what happens. So you have another very interesting, important equation from Euler. I think Many people call it the most beautiful mathematical equation ever, because then it includes practically all of the famous constants that we used to use in absolutely different ways in millions of different applications and different fields. They do not seem to be related at all. You have, in that equation, you have E, which is Euler constant from his name. This is related to logarithms. It's natural basis for logarithms, okay? This is E, 2.7 something. Then you have pi in it here, okay, which we know relation of the circumference to diameter of the circle, nothing to do with logarithms, right? You have that I or J, which is square root of -1. You have 0 and you have 1, like all of the main constants in the same formula. And all of them have no relation to each other except that formula. So it's interesting that he developed that type of relation. And this relation is very simply coming from his original theorem, right? You're just putting that e to the j pi. What does it mean, e to the j pi? So pi angle is negative direction of the real axis, right? E to the j pi sitting on the unit circle, which means it will be just number -1. So e to the j pi is like you're taking 180 degrees and sitting on unit sphere, so it's -1, real number. So -1, obviously +1 will be 0, right? This is that simple. Any questions on that? Okay, another thing that you need to remember is that all of the solutions for equations of that kind will have infinite number of solutions, because when you're moving on that sphere, you can move as many times as you want, and you can get that number 1,000,000 times, billion times, whatever number of times, each time you circle, but you get back to the same angle. So angle like 2 pi repeats itself all the time. Like, so everything which is working for 2 pi, for 0 angle, 2 pi angle, 4 pi angle, 6 pi angle, 8 pi angle, all of them are same number, right? So you can always write all of the solutions like that, like j theta plus 2 pi k, because it's all repeated after 2 pi. And k could be any positive or negative integer, 0 plus -1 plus -2, or any k, which is integer, okay? So all of these are repetitive. Any questions on that? Okay, I think this is the last thing that I want to talk about on complex numbers here. So you have absolute values, which is defined by those 2 bars around the number. And please do not mix that with determinants, because determinants also will have 2 bars, but on matrices. So absolute value is always positive, and by definition, this is for complex number, a square root, positive square root of a squared plus b squared, okay? Or r, in that case, for that representation. And this is why, because absolute value of that complex number, as you might remember from school, absolute value of multiplication is absolute values multiplied each other. Okay, so a, b absolute value is a absolute value times b absolute value. So you can divide it like that. So you get absolute value of r here times absolute value of that exponent, which is, we will prove that this is 1. Okay, so it will be just r. Since r already positive, it's radius of that complex number. And this is conjugate, I talked about that already. And geometrically, it looks like that. It's just mirror reflection with regard to the real axis. This is what conjugate is. So here is why that thing equals to 1. So we define that by Euler theorem as cosine theta plus j sine theta. But absolute value of that thing is square root of cosine squared plus sine squared. And as we've seen, this is 1. So square root of 1 is still 1. This is the proof, like why that works, okay? By definition of exponent from Euler theorem. Any questions so far? Okay, so now we are ready to solve the interesting example that I showed you that you cannot do without complex numbers, because this is the only solutions that you can have for that type of problem. I mean, probably you have other solutions, but all of them are going through some sort of complex numbers. And magically they somehow disappear eventually. And you get everything real, and the solution will be real. Okay, so the question was, you have nth element of that recursive sequence, xn equals 2xn minus 1 minus 2xn minus 2, and starting with some sequence of numbers for n equals like 0, 1, 2, 3, 4, 5, and so on. Okay, so it has that sequence of numbers. Now, to solve any difference equation, typically we use Z transforms, but you don't have to. You just need to guess solution. It's very similar to differential equations. So if you took course on differential equations, you know that for continuous differential equations, you typically use solutions with exponents. So you have some constant times exponent to the power of something plus some constant times another exponent to the power of something. This is your like best guess for solutions for linear equations, for linear differential equations. For difference equations, your guess is always powers of your variable. So you get some number to the nth power. This is your best guess, or some constant times nth power of that variable. Okay, so I call that variable z. Okay, and z is for a very simple reason, because it relates to z transform. If you learn signals and systems in electrical engineering, and you learned about discrete systems, something, you use Z transforms. And if you don't know Z transforms, that's fine. You don't have to know Z transforms. The only thing that you need to know about Z transforms, it's similar to Fourier transform, but for discrete type of things, that Z transform of delayed number x, okay, n minus some constant k, is Z to the power of minus k of the transform of the original Z sequence, okay? Not Z, X sequence. So you have sequence X, and if this sequence is delayed by K, in the Z domain, it will be just multiplication by Z to the minus K power. But you can do the same thing with just guessing that the solution is Z to the power of N of some kind, okay? Then you can put it here, you'll have Z to the power of N equals twice Z to the power of N minus 1, minus twice Z to the power of N minus 2. And then you can divide both sides by Z to the power of N, right? So you can cancel some of it. But we are doing just Z transform on both sides. Okay, so to do Xn Z transform, you'll have capital X of Z. Right? It's just direct transform. Whatever the sequence is just Z transform of that sequence X. Is it clear what I'm doing here? Do you remember what Z transform? Like, who knows what Z transform is? Okay, not many people know what Z transform is. Okay, so let's go the other way around. Let's try to write it down. You have right n equal n minus 1 plus n. One by x. Close enough. All right. So what happens is you're saying my xn will be z to the power of n. This is my guess. Okay. Or some constant times z of n, but this constant will not matter here because all of them are multiplied by the same constant. So it doesn't matter, constant will cancel. So this is my best guess. And again, in differential equations, you need to guess some stuff. So it's not directly that you have formula for the solution of that kind of thing. Then I will want to put it in. So I will say that xn, which is z to the power of n, equals twice, what is n minus 1? So I'm replacing that n with n minus 1. So z n minus 1. Okay. Minus twice z n minus 2. Okay. Now I want to simplify. So I will, let's say, divide by z. I want to cancel some of it. So I will divide both sides by z and minus 2. So I'll get here squared equals twice z to the power of 1, of course, minus 2. I just divided both sides by the same thing. Okay, so this is practically quadratic equation. E squared minus 2z plus 2 equals 0. So I can solve the quadratic equation. So z 1, 2 is the formula for quadratic equation. So it's minus b, which is 2 plus minus square root b squared, which is 4 minus 4ac. It's like 1 times 2 times 4, so it's minus 8 divided by 2a, which is 1. Okay. So you get 4 minus 8 is negative 4, so it's clearly a complex number. Right? You have complex roots for that thing. So you have 2 plus minus 2j divided by 2, which is 1 plus minus j. Right? So that's your solution of the quadratic equation. So your solutions will be 1 plus j to the power of n or 1 minus j to the power of n, and they will solve that kind of thing. So you can blend them all together like that. So full solution will be xn equals c1, some constant, times 1 plus j to the power of n plus c2, 1 minus j to the power of n. And how do you know these constants? From initial conditions. Right, so you have initial conditions. I believe it started with 1, 1, 0, I don't think it's 2, 1 actually, and so on. I actually need only 2 constants, so I'll be able to compute C1 and C2. So what I know is like x0 equals 1, this one, right? And this 1 equals to C1 times this one to the power of 0 is 1. Anything to the power of 0 is 1. Any complex number or not complex number, it doesn't matter. Plus C2 times 1. So it's like C1 plus C2. Right? So 1 equals C1 plus C2. We have to write the system of equations. So if x1, which would be again 1, second one, now, okay, equals C1 times 1 plus j. The first power is still the same thing. Plus C2, 1 minus j. First power. We'll have, one thing will be, let's see, C1 plus C2 plus C1j minus C2j. But this thing, we know that this is 1 from here. C1 plus C2, we know this is 1. So this one will cancel with this one. And you'll have C1 plus C2 times j equals 0. So practically C1 equals minus C2. That's the system of equations. C1 plus C2 equals 1, and C1 equals minus C2. So the solution is pretty simple. C1 equals C2 equals 1/2 for that particular initial condition. Okay, so far. And again, without that, you cannot get here somehow. Okay. But that's not all, because this looks very complex. Right, so we know now that this one is 1/2 1 plus j n plus 1/2 1 minus j n. And this looks very complex. But it's not, it's actually real. How do you know that this is real? Again, to do powers of anything, you need to convert it into polar coordinates. It will be much easier. So pay attention that 1 plus j is just that kind of vector. 45 degrees here. 1, 1. 45 degrees is pi divided by 4 angle. Okay, so you can write that thing as 1/2, and then you get radius is square root of 2, right? So you get square root of 2 to the power of n, and then exponent j n pi divided by 4. Okay? Because like n is coming from that thing, so you need the radius to the power of n and the exponent j theta to the power of n, and k is pi divided by 4. Okay? And same thing here. So this is just conjugate of that part. You'll have 1/2 square root of 2 to the power of n e minus j n divided by 4. Now, do you recognize what that thing is? So some exponent to the j theta plus some exponent of minus j theta divided by 2. What is that? It's cosine. So we have that earlier formula, e to the j theta plus e to the minus j theta divided by 2. This is cosine of theta. Formula. So our theta now is that thing. And you have that divided by 2 here, divided by 2 here. This is that thing. Okay. So you can write that thing here like that. You will get square root of 2 to the power of n, both of them together, and then cosine of pi n divided by 4. That's it. Right?
So when you were solving for the for the second equation, xn is equal to c1, why did you use plus j for the first x and minus j?
You are
for the
talking about
second?
this one?
No,
This one?
no, the next one.
This one?
Yeah.
Yes.
I mean, why didn't you use plus j first for both instances, minus j for next instance?
You're talking why I wrote that way?
Yes.
So when two solutions of some linear equation, because this is practically linear equation. So when you have two separate solutions of same difference equation, the linear combination is always also solution for that same linear equation. So this is linear combination of the solutions with some coefficients. I don't know what these coefficients are at that point, but it's something, some constant. It's superposition rule practically. So in the superposition rule, this always will be solution of that equation if each one of them is solution of that equation, whatever the solution is. Okay? So it works same way with differential equations as well. And it will be tricky to explain that, but this is where it comes from. Any other questions? Yes.
Maybe I'm misunderstanding, but in your system of equations for C1 and C2, how does C1 equals C2 equals 1/2 satisfy those equations? It satisfies the second one, but how does C1 equals negative C2 be true if you have them both equal to 1/2?
Because it needs to be minus here.
Oh,
This one.
oh yeah, yeah.
It's C1 minus C2.
Oh, C1 equals C2, yeah, yeah.
Right. This was wrong, yes.
Question about the third line. Is
What?
Third line. Z
Third
of
line.
n
This
equals,
one?
yeah, y we divided by z of power n minus 2. Why we divided by
To get quadratic equation, I guess. This is how you solve that type of equations. I just canceled it. I canceled that part. I needed to get rid of some of it.
Okay,
So
so
I
is it,
canceled that part practically. You can do that probably some other way by reorganizing it that way, so it will be easier to see, but just when you're dividing everything by z to the n-1, n disappears. So I want n to disappear. I could keep it other way around. I could divide, for example, by 0 by n to the power of n, right? So it would be 1 equals 2z negative 1 minus 2z negative 2, right? And then I need to solve that kind of equation. I just need to get rid of m to solve that equation, right? So I can get rid of it in multiple different ways. I think this one is the easiest one, just to divide both sides by that thing.
So the third line is all divided by z of.
Yeah, so I divide this one by z to the n-2, this one by z, n-2, and this one by z, n-2. So I can practically divide by anything, right, except 0. I can divide by anything, but this gives me the benefit that I'm getting rid of m in a quadratic equation. The idea, yes.
So should we have had a cubic equation? This second equation would have been a linear combination of the three.
It will be linear combination of 3, yes. You have additional components like n-3 somewhere, you get cubic level, then you get all of them, yes. You get all of the solutions as linear combination is C3, and then you need also third number in the initial conditions. You need 3 initial conditions for cubic one. Other questions?
Where the initial conditions always been provided.
For that kind of equation, you have to, otherwise, how would you compute any differential equation or difference equation without initial conditions? Solutions will be very different from different initial conditions. Yes, they always will be provided, yes. A few more slides on algebra. Just for you, let me show the screen.
And then it said you have to extend the controller, else the recordings will cease.
I hope it is recording all of it.
Yeah, but when you were writing, they gave a notice that the recording will stop in the next 10 minutes, which is the next 4 minutes, unless you extend it.
We'll see how it works first time doing that on the board. Okay, so the idea is that you have basic rules of algebra. Again, you need just to know and remember terminology. You have commutativity rule, where you can switch between in sum and multiplication between the variables, order of the variables. A plus B equals B plus A, or AB equals BA. In algebra, multiplication will not work. So in linear algebra, you will not have commutativity rules for multiplication. So AB will not be BA. Very important to remember that you cannot switch order of the matrices when you multiply them. Associativity will work, which means you can put parentheses to any pair wherever you want it for addition, and same for multiplication. Same will be in linear algebra, same rule. Distributivity is very important rule, how to open parentheses practically when you're multiplying. And in regular algebra, it doesn't matter from which side you multiply by the third variable. It could be like A plus B times C, or it could be C times A plus B, because you can always switch. In linear algebra, you cannot switch. So you will have multiplication from the left, and you will have multiplication from the right. But distributivity rule will still work for both. Okay, you still will be able to open parentheses the same way like you're opening them here. So this is distributivity. And fractions, you can always multiply and divide by the same number, so you can cancel fractions. And to multiply two fractions, you just multiply numerators and multiply denominators. To add fractions, you're making common denominator, just to remind you, like that. And then you can just, why this works, this is the explanation. Just multiplying by the same number, numerator and denominator, which is not changing anything. And then you get common denominator for both of them. And probably will not have much time today to work on theory of sets, so we'll start doing that next time. Questions? All right, thank you.